Alright, this is homework 4, part 3. We are going to be performing a von Neumann stability analysis to show theoretically the limit of stability on the explicit differentiation scheme used in part 2. So, let's get started. So our first equation here is the differential analysis, not the differential analysis, it was the heat diffusion equation from Cartesian coordinates, which we solved in part 1. And we solved for t outside here. That's what this is right here. That's not the solution for that isn't important to the problem. That's why we're not solving that. But that's given right there. That's what that is. And then when we use, and then after that we solved the differentiation here to get this equation, which we graphed and coded. And when we graphed it, we realized that if we had a time step greater than 0.5 seconds, the graph was nonlinear and unstable. So we are going to perform an analysis, a von Neumann analysis, to prove that that is in fact correct. So the first thing we need to do is look at this t value here and substitute into it this explicit differentiation that we did in part 2. So let's get started. So the first thing to notice about the t values down here is that they have j and n units. Now j is a position unit, which we know is delta x. So delta x times j is what that is. And then for temperature, our value is n. So that's what that is. So when we plug in these values for t, we just need to substitute in these values for x and t. So that is, let's start with just j and n, make it simple to start out with. So we know from above that that's going to be E is equal to I times k delta x j, and then that is times e to the negative alpha k squared delta t n. Now for the example of j plus 1, we are going to have e to the I times k delta x. But then, since it's this is the plus 1 term, and then the whole thing is repeated, so then we can just multiply that by j times n. So, again, just to reiterate, this is the plus 1 term, and then the rest of it, the j plus n, we could just repeat that instead of having to rewrite the whole thing. That's what that is. And then if you were to have j minus 1n, that would simply be e to the negative I k delta x, and then this repeated. So if we want to put all of this together, we would be left with t to the j n plus 1 is equal to r, no, we want this on the outside. So this is going to be t j n. You're going to be left with r, this one because the first term is plus 1. So r e I k delta x. And since we pulled t j n to the outside, so we didn't have to multiply that on the inside. And then we're going to have 1 minus 2r, and then plus e to the negative I k dx. Alright, perfect. Now we need to discuss Euler's formula in order to solve this any further. Euler's formula is e to the e to the I times x is equal to cosine of x plus I sine of x. Now this is significant because each one of these terms has an e to the I x term. So this one is good for our positive term, but for a negative term we would have Cosine stays the same. This is going to be minus I to the sine x. Now basically all we need to do is add these together. The signs cancel. And we are left with a very simplified equation, which is t to the jn plus 1 is equal to t to the jn times 1 minus 2r plus 2r cosine to the k delta x. So does that make sense? Basically, we substituted e to the ix with Euler's formula, and obviously we have k in there, so we had to throw k down into the bottom, which is basically just the x term, and we got the signs to cancel since we have a positive and a negative value of e ix. So that actually works out very nicely. And so from here, what do we know from here? Now from here, we need to determine a limit of stability. We do know, just from looking at this, that this can't be more than 1. If this term is more than 1, this term is going to go to infinity or negative infinity very quickly. So that just means that we need to ensure that this stays below 1. So let's define a limit of stability. This is 1 minus 2r plus 2r cosine k delta x. And this is has to be less than or equal to 1 and greater than or equal to negative 1. And now we can divide 1 for both sides, so we have something that looks like this. And then since there's 2r can be distributed to both terms, so then we can be left with 2r cosine k delta x minus 1, and then with the limit negative to 0. Now looking at this term, we know that this term is always negative, because cosine is either 1, can go from 1 to negative 1, and if it's minus 1 and it's positive 1, it's just 0. And then, yeah, basically we just know that this is always negative. So we really don't even have to worry about this limit on this side. It's not something we need to worry about. And we know that r, well, what can we do next? We can, alright, so we need to get r by itself here. This is the next step. So we're going to be left with something that looks like this. X. K delta x, this is always going to be either the highest values are 1 or negative 1. So we can simplify that down to 1 over 1 minus cosine k delta x squared is equal to r. And since we know that cosine of k delta x is either equal to 1 or negative 1, those are the highest values. When cosine goes to 1 is 1, this is 0, so that would mean it's nearing infinity, which we don't want. But when it's negative 1, that means this is going to 1/2, which is exactly what we got for the step in the last part, which confirms what we had. So this is exactly what we wanted. Now I kind of forget if this is the right part right here. If we made this right step, I know that this is what we needed to get to. So I'm gonna go check that real quick, and if I find that I did something wrong, I'll come back and explain to you what I did incorrectly. Nope, I was correct. I just am not very good at algebra, so I was confusing myself. However, this equal sign is not equal sign. It is, in fact, a greater than or equal to sign. So R must be less than or equal to 1/2. And just a reminder that from the last part, our time step had to be 0.5 seconds, which is 1/2, obviously. And R is equal to alpha times the time step over the partial derivatives there. No, alpha would, yeah, C2 yes. Sure. So that's what that is. So that confirms our von Neumann stability analysis. Thank you.